Hello everyone, and welcome to our presentation on the paper using Prosody to improve dependency parsing, which is part of the work that I have done with Michael Mandel as part of my PhD dissertation under his supervision. The main goal for this is to improve automatic syntactic dependency parsing of spontaneous spoken sentences by making use of prosodic cues. The main motivation for this is that automatic parsing has been shown to be negatively affected by the presence of syntactic ambiguities, while on the other hand, it has been also shown that prosody sometimes helps resolve some of these ambiguities. In addition, syntactic structure has been also shown to have some kind of relationship with prosodic structure. As we can see in this slide, both syntactic structure and prosodic structure consist of a hierarchy of constituents. However, the prosodic structure is much flatter than the syntactic structure and with less recursion. It has fewer categories such as intonation phrase, intermediate phrase, and phonological phrase, and prosodic word. Our main focus in this work is on prosodic phrasing, which is the segmentation of speech into prosodic units and the boundaries between such units, which are referred to as prosodic breaks or prosodic boundaries. The prosodic breaks are acoustically associated with things such as the silent intervals or pauses between words and the duration lengthening of pre-boundary syllables. In terms of annotation, prosodic breaks are represented on the ToBI annotation system in terms of break indices, which take values ranging from 0, indicating that there is no break or no disjuncture between words, and 4, meaning that there is a strong break corresponding to intonation phrase boundary, or 3, which corresponds to intermediate phrase boundary. There has been a number of approaches that attempted to use prosody to improve parsing. Most of them focused on constituency parsing, while one approach attempted to look into dependency parsing, and we will see the difference in a minute. It is important to point out the difference between constituency parsing and dependency parsing because we are using dependency parsing unlike most of the literature. For constituency structure, we see that it is made of a hierarchy of constituents, such as a sentence, a noun phrase, and verb phrase, and all of the other categories, in line with phrase structure grammar. And the way to measure how good a constituency parser is by comparing the parse, how many categories or constituents have been correctly predicted by comparing to the ground truth or the gold standard. And this is as we've seen, this is the most popular in most areas of linguistics, including the area of studying the relationship between prosody and syntax. However, the dependency structure, it is much leaner structure, which includes mainly the information about each word and the head of the word and the relationship between the two. And it has the same kind of information that the constituency structure has, in addition to the head information. And the main metric is the unlabeled attachment score, which represents how many heads did the parser predict correctly compared to the gold standard. And it has some advantages of being faster than constituency parsing and more scalable to new languages using what is known as universal dependencies, in addition, of course, to capturing the semantic information between words. Our hypothesis for this work is twofold. First is that there is some kind of correspondence between prosody and syntax that can be extracted from the dependency structure. And the second is that these correspondences can be used along with prosodic information to allow us to select the most likely parse for any given sentence by selecting from a number of parse candidates or hypotheses. The data we're using here is from the Switchboard corpus for conversational speech. The syntactic information for this corpus has been converted to dependency format by Honeybell and Johnson, and a subset of this data is manually annotated with ToBI annotation, and we are using this for our analysis. There have been some early work to suggest that dependency information can have some kind of relationship to prosody. One class of approaches in psycholinguistics attempted to use syntax to predict the likelihood of prosodic breaks. Two notable of these approaches were by Ferreira 1988 and by Watson and Gibson 2004, where one common theme is that there is less likelihood of a prosodic break between two words if there is dependence between these two words, or there is some kind of semantic coherence between them. And these ideas are based on the notion suggested by Selkirk in 1984, which is known as sense unit condition. In our study, we introduce a new notion, which we refer to as dependency configurations, to capture and describe the dependency situation between two consecutive words and how this can be related to prosody. In this example, we see the dependency structure of the sentence is that what you're saying, where the dependency structure identifies the head of each word. But if our unit of analysis is the pair of words, such as is that and that what, and so on, we have four possibilities for each word in each pair. The head of the word in the pair can be either the other word of the pair, which is partner, and in this case we call it P, or that the word has the head to the right of the pair, and in this case it will be R, or to the left of the pair, which it will be L, or that the word is the head of the sentence or the root of the sentence, and in this case we use it O. This would lead to a pairwise notation where, for example, it would be something like P and O for each pair, and this is what we refer to as dependency configuration. Based on the data from the switchboard corpus that was converted to the dependency structure, we find 12 possible configurations, which can be grouped into 4 categories. The first category is what is referred to as L and R, left and right, where the first word in the pair depends on the word to the left, such as the word that, which depends on is, and the second word depends on a word to the right, such as what, which depends on saying. The second category is that there is no direct dependence. For example, the pair of words what you, the word what depends on saying, and the word you also depends on saying, but there is no direct dependence between the two words. The third category is direct dependence, where one word in the pair depends on the other word, such as are here depends on saying. And there is a fourth category, which is unusual, if in case that there are two roots in the sentence rather than one, which mainly happens because this is spontaneous speech. Analyzing dependency configurations against ToBI break indices in the data, we find some interesting patterns. One of the important patterns is that the category and configuration L and R accounts for a lot of the ToBI breaks 3 and 4, and also the category no direct dependency, which includes a number of dependency configurations, also accounts for a large number of ToBI breaks 3 and 4, while the situation where there is direct dependency, it accounts for less. Taking it from the other way around, meaning that the probability of ToBI break 3 or 4 given the configuration, we find that the configuration category L and R associated with the largest conditional probability for both 3 and 4 ToBI breaks, followed by the configuration no direct dependency, and then the configurations where direct dependency has the least likelihood of having prosodic breaks 3 and 4. Moving on to the next part of the presentation, which is actually how to put these insights into an approach to improve parsing. The main goal of this work is to build a system that allows us to use the output of a number of automatic dependency parsers and score them using a neural network classifier to allow us to select the most likely parse for any given sentence. In order to do this, we extract the text information from each parse hypothesis, in addition to the prosodic information from the annotation that comes with the switchboard corpus. Our classifier would predict the compatibility between prosody and the proposed syntactic structure proposed by the parser to identify the most likely parse given the prosody. So the features that we are using as part of this system are either text or prosodic features. The text features come directly from the parse hypothesis and includes the parts of speech tags and the dependency configurations which we discussed, in addition to the word embeddings related to each word and the head of this word. The other category we have here is the prosodic features, which include the normalized word durations, and we do this by dividing the value of the actual duration of each word by the expected duration given the patterns of each speaker. And in addition, we also use the silent intervals or pauses between words. And this is an example of the kind of features that are extracted from this parse hypothesis, showing the text features which are either lexical, meaning the word and the head of the word, and which are converted to word embeddings, and the syntactic, which are the parts of speech and the configurations, in addition to the prosodic features which have the normalized duration and the pauses after each word. These features are extracted and then fed into neural network, and here we use recurrent neural networks because it's very flexible by accepting input of variable length, such as sentences with different lengths, and we use the long short-term memory optimization, LSTM. The system works in two stages. The first one is the training stage. In the training stage, the system is fed with each parse hypothesis together with the acoustic information of the sentence, and it extracts features from them. In addition, it's also fed the correct or the gold standard parse, where it compares the parse hypothesis with this gold standard, and this is the outcome to be predicted by the network. And after feeding all of the sentences with all the parse hypotheses multiple times to the network, it is now able to identify the patterns and generalize to data that has not been seen before. And at this point, we use it on the testing stage. So we feed it the testing data, the parse hypotheses in the testing data, and it allows us to score each parse hypothesis in sentences that have not seen before by the system. And this is where we get the system to actually score each parse hypothesis and give it a number to allow us to select what is the most likely parse hypothesis given the set of features that were fed to the system. And in this case, we see that the system was able to predict the most likely parse, which was actually the best parse given the US value by comparing it to the gold standard. And these are the experiments that have been run on the data, showing the best individual parser was clear NLP, as shown from the US value for both the development set and the test set. And we show also the Oracle score, which is the upper bound of what can be achieved by this system, given that these three parsers. And then our experiments with the ensemble, showing an experiment with only the text features, the parts of speech and the configurations, indicating an improvement of almost 1% above the best individual parser. And when we add the prosodic features, the duration and pauses, we have an additional 0.4 to 0.5% improvement in the parse US output. Going further, we also tried to use the lexical information, mainly the word embeddings, and these have led to a much higher improvement in both the US and the development and the test. And at this point, there was very little margin for improvement by using the prosodic features. So the main conclusions for this work is that some syntactic information, which are mainly the dependency configurations that can be extracted from the dependency structure, actually relate to the prosodic breaks. and using this information together with the timing, mainly the pause and duration, is more useful for selecting better parses than the syntactic information only. And the ensemble system in general yields better performance than any individual parser in the ensemble. Thank you so much. Please let us know if you have any questions. Thank you.